introduced the study of the dynamics of astrophysical fluids. In particular, we've been focusing on ideal fluids. So, but this, then I will remind about this. So far, we saw the continuity equation, which is just a very general equation in physics that you've met repeatedly, and also in this very course, when we talked about the equations describing the electromagnetism. So in that case was the conservation of charge, in this case, the conservation of mass. Conservation of mass, which holds as long as we do not consider special relativity. So this is just in the Newtonian regime, which is exactly what we've been doing so far about astrophysical fluids. The very last thing we saw is just the equation of state, which is an equation with connecting density, pressure, and temperature. So the thermodynamic, the macroscopic thermodynamic quantities which describe the status of the fluid. Next step is the so-called Euler equation. So what is that? Well, it's just a matter of applying the second law of dynamics that you know very well to a fluid element. Again, an ideal fluid element. So no shear strain, no shear stresses, and no heat conduction. But this is something that then I'll comment again. So what am I supposed to do? Well, just take and let's consider a volume element dV. Rho is the density of the fluid, so rho dV is just the mass element. So mass, the element, the mass of the elementary element that we consider times its acceleration. So this capital D, dOV, its element.
Prof, mi scusi, ha ripreso ad andare a scatti.
Va meglio così? Is it better now?
Maybe yes.
Little better?
Maybe. No. Yes, it is better. Thank you.
Okay, thanks for pointing out.
No problem.
So this is just second law of dynamics. So we have to put all the forces acting on this element. So what are they? Well, first of all, we have to assume that there is some force field. In particular, given that the fluid just are not discrete elements of mass, so we define F as the force acting per unit volume. Okay. So given that dV is the volume of the element that we're considering, just F dV, just like that. But then there's also another force that you should remember when talking about fluids. If pressure has some gradient, so if the pressure gradient is non-zero, well, the minus gradient of pressure is also the force acting per unit volume. So pressure, okay, is all the volume
Prof. Scusi se la interrompo. Prof, mi sente?
Sì.
Ha ripreso ad andare a scatti, non so se sono l'unica, però...
Confermo, anch'io sento a scatti.
Anch'io, prof.
Mi sentite male?
No.
Proprio male? Sì, allora evidentemente la mia rete. Questo è un bel problema. Continua ad andare male?
Ora no, va e viene.
Esatto, riprende ad andare bene per circa meno di un minuto e poi riprende ad andare a scatti e peggiora.
Allora, vi propongo questa cosa a questo punto. Io provo ad andare avanti per 10 minuti e voi mi fate presente come state facendo già adesso. Se la cosa sembra non risolversi, allora io poi chiederò che la registrazione venga cancellata, cancello la lezione e rifaccio la lezione in presenza, e a questo punto metto anche in discussione un po' tutto quello che è il discorso che vi facevo l'altra volta, perché è chiaro che se la mia rete diventa così instabile non posso fare lezioni da casa.
Ascolti, prof.
D'accordo? Sì, prego.
Potrebbe provare, secondo me, a vedere se riesce ad utilizzare l'audio da telefono. C'è questa possibilità con Meet. Se lei,
ecco, questo non lo
se lei
sapevo.
va nelle impostazioni, nei 3 pallini, insomma, a un certo punto dice utilizza un telefono per l'audio, magari quello potrebbe aiutare a liberare un po' la rete.
Lo vedo effettivamente. Va bene, allora facciamo così. Se il problema si ripropone nei prossimi minuti, proviamo questo estremo tentativo che tu suggerisci, anche se devo capire come si fa. Quindi,
Ok.
d'accordo?
Sì.
Va bene. Scusatemi per questa cosa, ma purtroppo è una novità spiacevole anche per me. Ok, so we were here. So this is just the second law of dynamics applied to the volume element. Okay. So no shear stresses. So just the surface forces acting on a generic volume element. We just consider those the one due to pressure. So no shear strains. So what is the capital D? What's this kind of derivative? Well, you have to imagine that you have to calculate the acceleration of the generic volume just by chasing him. Ideally, you have to look at you identify a given element of fluid, and then you ideally follow in its along its trajectory. So this derivative is just the so-called total derivative or material derivative, also convective derivative, because it's just the idea is just, as I say, to ideally follow this the element of fluid that you identified as a while during its motion. So convective also from Latin convere, which means to transport. And what is that? Well, you have to imagine that, of course, this function v, the velocity that you are time deriving, is a function in the most general cases of the spatial as well as of the temporal component. So its total derivative is just this partial derivative with respect to t, the first term, plus what? Well, given that you are ideally following the element, it is as if you were considering all the spatial coordinates x, y, and z as function of time. So derivative of derivative. So derivative with respect to x times the time derivative of x. And so the same for also the other coordinates. So this total derivative of convective derivative, which usually it is denoted with capital D, is nothing but this, which can also be summarized as this guy here. If you look, it acts on a scalar function, and you can summarize as just the second term, the spatial term, as velocity scalar, the gradient of this function. Okay, so in this case, the velocity itself. So what does this mean in particular? If you look at here, well, derivative of velocity, gradient of velocity, gradient of a vector. No, it means that you have to consider one component, one Cartesian component at a time. So rewriting the second law of dynamics applied to it means, and dividing by, well, you see, you can just remove dv in both sides of the equation, and then dividing by rho, you have the total derivative equal 1 rho or here. So explicitly what So the total derivative is just the partial derivative with respect to time plus this term, this one. But again, do not make sure you're not confused by this writing, by this notation. So what is gradient of a vector? Well, it means that this is a vector equation. So they are all vectors. So also this, which is a scalar product, should be a vector. So it means that, as a matter of fact, when you project this equation, for example, along x, it means that here you have to consider the gradient of Vx, so the x component of the velocity. So a good exercise is to write it explicitly to make sure that you are in control of the thing. So you see, when you project the entire equation along the x, it means that here is nothing but the gradient of Vx. Vx is a scalar function, of course, is the x component of the velocity as a function of space and time. And so this is just, as I said, so you can immediately see that that's exactly what I just said. And then the other vector, I just took the corresponding component, whether it is x, y, and z. So moving on, let's consider some interesting case. So for example, when in the case of spherical symmetry, so getting back, you see, if you write this equation in the case of spherical symmetry, it means that V is a function which only depends on R. There's no theta and phi dependence, okay? So it means that here, the only component which survives is the gradient of the radial component of the velocity. So again, in this case, the gradient is just dv over dr times v. V is, I don't need to put vr as the only component surviving, so the radial component. And then, of course, the gradient, the pressure gradient is just the only component due to, again, spherical symmetry, is just dp over dr, as well as the component of the force field. If, let's make an additional assumption. Let's assume that there is no, but the flow is steady. Steady means that if you fix at a space, in a point in space, there is no time dependence. So the partial derivative with respect to time is 0. So there is no explicit dependence on time. So it means that this guy here is 0. So again, on the left side, on the left-hand side of the equation, the only non-zero term is this guy here. And here I just, instead of partial, I just put the total derivative, but simply because v is just a function of r, so is a function of one single variable. So you don't need to write the partial notation. And again, for this very same reason here, so both functions, of course, the velocity as well as the pressure are just a function of r. An example of this is, for example, when you are not considering not a generic force field, but for example, in the presence of just gravity. So the only force acting per unit volume is the one due to gravity. I remind you, we define Fr as force per unit volume. So it means that the case of gravity and spherical symmetry, you know very well that because of Gauss theorem, this is just minus g m star. M star is the mass contained within a sphere of radius r, so over r squared. It should be rho times rho because it's force per unit volume. But this is over rho, so just rho cancels out. And in particular, when you have no velocity at all, so you have hydrostatic equilibrium, so all the fluid is steady, doesn't move. So it means that velocity is 0. So the left-hand side of this equation is 0. So you see, you end up with an equation that you should be already familiar from stellar evolution studies. So all the equations that rule the stellar evolution. And again, this is you can look at this as a special case of linear momentum conservation. In general, you know, linear momentum conservation is just the consequence of second law of dynamics. So given that what we derived, which I forgot to tell you, it's called Euler equation, is just the corresponding equation that rules conservation, the overall conservation of linear momentum. And okay, so moving on, we'll obtain a result, a generalization of a result that you know very well from your previous studies, but put in a more general context, which is Bernoulli's theorem. To do that, let's define the so-called vorticity. So let's suppose we have a field of velocity, a velocity field which describes the velocity of our fluid. Let's define the curl of this vector of this velocity field as omega, and we call it vorticity. Why? Well, because if vorticity is non-zero, because of Stokes' theorem, it means that the curl of the velocity field is non-zero. It means that there are some closed paths along which you have some current. So you have some vortices, because in this case, the vector field we are thinking of is just the velocity of the fluid. So if you think of Stokes' theorem, you immediately see that non-zero vorticity implies that you have some vortices. So the fluid is just flowing within some closed lines, so a vortex. Let's consider the vector product of V vector the vorticity. And just by definition, this is this guy here. But then we can exploit vector calculus identity. So this guy is V times V scalar V, and then gradient of, so gradient of V squared, essentially, minus the first scalar, the second, the third. So V scalar gradient of what? Again, the interpretation is that you get Vx, and then you work out the gradient, and then times scalar V, and so on. So one component at a time. Okay. So having seen that, we consider the F, as I told you before, is the force acting per unit volume. Let's consider a conservative field. In particular, by dividing F over ρ, well, F is the force per unit volume. If you divide by the amount of mass that you have in the unitary volume, which is ρ by definition is the density, it means that this guy is the force acting per unit mass. But given that it's a conservative field, that's the assumption we are making, there must be some potential associated such that minus gradient of phi is the force per unit mass. So the potential is the potential per unit mass, okay? Now, let's put all this into the Euler equation we've just seen. So the time derivative, or the total derivative of the velocity, it was F over ρ, and this is just minus the gradient of the potential, so minus gradient of phi, and then the same guy here that we had before, minus gradient of P over ρ. Now, let's consider this guy here, V scalar gradient of. This is the guy we have here, if you look. So we can express this guy as this one minus this one, which is exactly what I did here, because you have 1/2 gradient of velocity squared half, which is this guy here. And then I took this and put on the left-hand side of the equation, so plus gradient of phi, and then minus V times V vector omega, this guy here. So I just replaced with this guy, this term here and this term here, and just put minus gradient of phi on the other side of the equation. So I included in this term. And then I also put this guy here on the left-hand side of the equation, so plus gradient of pressure over ρ. So I rewrote essentially Euler equation exploiting this identity, this calculus identity, okay? Now, let's make some further assumption. Let's consider the case of a steady flow. So as we did before, again, there is no explicit dependence on time. So it means that the partial time derivative of v is just 0. And the second batch of assumptions, which is very important, is the following. So again, we remind ourselves that we are limiting to ideal fluids. So in particular, we neglect both viscosity and heat reduction. So all the processes that can contribute to give an irreversible character to the transformations that the fluid can undergo. And in addition to this assumption, we assume that radiation losses are negligible. So you know very well the way a given thermodynamic system can exchange heat is either through viscosity, heat conduction, but also by radiating. So we make a further assumption. So we consider that the possibility of the fluid to lose energy by radiating it is negligible. And this is often the case in astrophysics. So this is not a so completely unrealistic assumption. So if you put together all these assumptions, you see that we are left with reversible transformation, which are also adiabatic, because essentially there's no way the fluid can exchange heat. So no heat exchange, and we also consider all the irreversible transformations, so all the effects that can make it irreversible. So reversible adiabatic, well, that means that the entropy that we can associate to the fluid is conserved. So if you focused on a fluid element and you follow it as time passes, the entropy associated to that element will be conserved. So if I call S the entropy per unit mass, the S, so the variation of entropy along the trajectory of the element, is 0. Let's remind ourselves and let's define some thermodynamic quantities that you should somehow be already familiar with, but I make a reminder. So let's consider in particular W. By the way, I'm following here the treatment, the notation by Vietri, okay? Because some notation can change. For example, the quantity that I'm going to introduce right now in many textbooks, it's denoted with H. Here I'm following just Vietri. So what is W? W is epsilon plus PV star. Well, what are they? Well, S, as I said, is the entropy defined per unit mass. Now we define enthalpy, W, which is also defined per unit mass. And epsilon is the internal energy per unit mass. V star is the unit volume. So the volume taken by a unit mass. So by definition of density, if you think, it's nothing but 1 over rho. So V star is the volume of a unitary mass. So 1 over rho, just like that. Now, if you remember, the definition of enthalpy is internal energy plus the product of pressure and volume. So given that all these quantities are defined per unit mass, that's exactly what I did here. So in particular, instead of V, in the fluids, typically it's more convenient to define an intensive quantity. So density rather than the extensive analog, which is the volume. So in this case, we are reasoning for unit mass. So V star is just 1 over rho. Okay. So this is a reminder of the definition of enthalpy, which, by the way, is one of the for thermodynamic potentials. With myself in your previous course, we met, of course, the internal energy and enthalpy. There are also other two thermodynamic potentials that I assume you will be studying, presumably in the statistical course by. Okay, so let's work out the corresponding elementary quantities. So, okay, let's have a look here. D epsilon, so internal energy. I remind you, we are considering reversible transformations. So you can immediately exploit the first law of thermodynamics, which I remind you is delta Q, if delta Q is the elementary heat exchange, minus P dV star. First, so instead of D epsilon, I just exploited the first law of thermodynamics, where instead of delta Q, I already exploited the reversible character. In particular, using second law of thermodynamics, you can express delta Q as T ds, where ds is the entropy variation. I'm not yet exploiting the fact that ds is zero. I'm still on a little more general level. Okay, I'm only exploiting the absence of irreversible transformations. So, and then of course the second one is just these two guys here. So you immediately see that this one cancels out with this one here. So you're left with TDS plus dP. So instead of V star, 1 over rho. Now we exploit the fact that we are neglecting any possible heat exchange. So this means entropy is conserved. Adiabatic reversible, so entropy is conserved. So in particular, the first term here is 0. So you're left with the change in enthalpy is just related to the change of pressure over rho. Okay, now let's consider the corresponding time derivative, total time derivative. Here, I use the small d instead of the capital D. But it's exactly the same, okay? It's total derivative. So it's the way enthalpy changes when you move along the trajectory of the generic fluid element. So if you want, it's just a matter of dividing by dt, just like that. You see, I just divided by dt both sides of this equation. But I remind you, the total derivative is the partial derivative, time derivative plus the scalar gradient. That's what we've seen. Where the assumption number 1 tells us steady flow, so all the partial time derivative is 0. So this guy is not here. So by replacing this guy here and this guy here, dV, the total time derivative of enthalpy, is nothing but the velocity scalar, the gradient of enthalpy. And here the same, 1 over rho times V scalar, the gradient of, well, of pressure. You have the time derivative of pressure. So we obtain this guy here. So this relation between enthalpy and the remaining quantities. So here I just copied what? If we get back for a moment, the equation we've come up with, which is essentially Euler equation, so conservation of momentum or second law of dynamics, and this identity, which, well, this is not an identity, this is in the assumption of reversible adiabatic processes, okay? So this is the thermodynamic part. So you see that here you have both terms which describe the dynamics, and also, since the pressure gradient comes into the dynamics, there's also this term. Now, let's consider Euler equation, and we multiply. We take V and multiply scalar all this term. So this guy is 0 just because we are in the steady flow case. So this is 0. Then I have V scalar, all this guy, so I just copied here. v scalar gradient, so v squared half plus 5. And then what? Well, I have v scalar, this guy here. V scalar, this guy here is
Prof.
equals v scalar.
Prof. Scusi se la interrompo.
V scalar,
Mi sente?
sentite?
Mi sente, prof? Ok, mi
Sì,
scusi.
adesso ti sento.
Scusi se la interrompo. Allora, finora è andato abbastanza bene, ogni tanto va ancora a scatti, adesso stava peggiorando moltissimo. Prima più o meno era sempre comprensibile tutto.
Allora, siete d'accordo? Facciamo così. Io provo adesso a far seguire come si fa con il telefono. È una lezione un po' disgraziata questa.
Sì, anche perché è la prima volta, le scorse volte non abbiamo mai avuto problemi nel sentirla.
Infatti, vi assicuro che ok, allora non so neanche io se fermare la registrazione perché sta venendo un po' una lezione un po' tribolata. Ok, allora facciamo così.
Forse c'è anche un altro modo, piuttosto che usare il telefono proprio solo per l'audio così, lei potrebbe accedere da telefono a questa stessa lezione, ok? E utilizzare i 2 account contemporaneamente, però a quel punto deve attaccarsi alla rete del telefono e non al suo wifi, direi.
Sì. Questo è un buon suggerimento. Allora provo a fare così, guarda. Ho in effetti questa possibilità, non c'è problema. Vediamo se disabilitando quindi il traffico audio ok, faccio così. Allora adesso chiudo il microfono mio qui e poi mi collego col telefono.
Ok.
Mi sentite?
Sì, ma con un
C'è un eco
poi
incredibile.
Va meglio così?
Sì,
Sì, decisamente.
ok, ci siamo.
Sì, ho dovuto chiaramente chiudere il loop se non lo facevo. Va bene, allora sperando che mi scuso ancora una volta la lezione tribolata, se ci sono dei problemi io adesso vi parlo dal telefono, naturalmente, quindi va bene, insomma si fa per dire. Ok. Allora, dicevo, I was saying, okay, so essentially, you see that we replaced the product of V scalar gradient of pressure over rho with V scalar the gradient of the enthalpy. So I can collect here the second term here, and then you see the last term is V scalar this guy, but you immediately see that V scalar something which is perpendicular to V is 0. So we are left with V scalar the gradient of just one single scalar quantity. But that means that this quantity is also the total time derivative of what you have among brackets, if you think, because the total time derivative should be V scalar gradient of something plus the partial time derivative of the same something. But we are in the steady flow, so V scalar gradient is just the total time derivative of what? Of what you're having among brackets. So it means that the total time derivative of what lies within brackets is constant. So is conserved along the trajectory of the generic fluid. So if you follow a generic fluid element along its trajectory, so you will see that the scalar is conserved. So let's have a look at the scalar. We call this B, capital B, and here I simply explicitly wrote what the enthalpy is. So the enthalpy is internal energy epsilon plus P over rho. So this is constant along a so-called streamline, which is, as I said, the trajectory of any generic element, fluid element. Why is this a generalization of Bernoulli's theorem as you saw it in your previous courses? Well, if you imagine that it's a generalization, first of all, because there are a thermodynamic quantity, which is the internal energy. We didn't consider at the time. We didn't consider the thermodynamic aspect. The second one is that in the case of an incompressible fluid, it means that density is also constant. So if you multiply B, which is constant along a streamline, by rho, which is also constant in the case of incompressible fluid, you find 1/2 rho V squared plus the internal energy epsilon rho plus pressure plus the potential energy plus per unit, in this case, per unit volume, if you multiply by rho. So that's exactly the way you remember Bernoulli's theorem. So this is a generalization. And in particular, you can make so I remind you, along the streamline, the entropy is conserved. The entropy per unit mass is conserved because of the assumption that we made. But if we make a even stronger assumption, so not only entropy is constant along the streamline, but it has the same value for all the different streamlines. You see that this is an even stronger assumption. And in this case, we speak of an isentropic fluid. So entropy is the very same for all these streamlines, so in every point in space. Well, in that case, if we just get back to the previous case in which we found, okay, I can do that, no problem. So here, look, where we derived this guy here in this yellow box here. So the total change in enthalpy is related to the total change of corresponding total change in entropy and pressure, like this one here. So it means that this guy, if you make it explicit, so it means that the change in enthalpy when you move along space is just its gradient times dr. There is no temporal change. We are in the steady flow case. So the only change is possible is just if you move, for example, by a small displacement dr. So dr, you move that, so then the change of the function is just gradient of the function, scalar, the small displacement. So the same holds also for the other two quantities. It was ds, so ds is gradient of entropy times dr, scalar dr, and so the same works also for the second term. But again, if we are in the isentropic fluid, it means that the gradient, since S is the same in every point in space, it means that its gradient is 0. So it means that you have just two terms. You can bring this one on the left-hand side of this equation. You can collect this guy here, but this must hold for any generic displacement dr. So the only possible way this equation is satisfied for any generic dr, it means that the first term among brackets has to be 0. So it means that there's, in this case, in case of an isentropic fluid, this identity must hold, which is stronger than this, if you look. This is a more general one. This is in the case of isentropic fluid. But again, let's have a look at B. If I work out the gradient of B, well, okay, it's the gradient of this term here, plus this term here, plus the gradient of this guy here. But this guy here is enthalpy, which is here. But now I can exploit this identity. So instead of gradient of enthalpy, gradient of P over rho. But look at here. The gradient of this term here plus this guy here, this guy is 0, is nothing but V vector vorticity. So it means that in the case of a null vorticity, which is also said to be, when the fluid is said to be irrotational, so no vortices. So when the vorticity of the fluid is irrotational, is 0, so the fluid is said to be irrotational, and the fluid is isentropic, you immediately see that B, the gradient of B is 0 in every point. So it means that not only is entropy not only does entropy have the same value in every point, but this holds true also for B. So this quantity is the very same. We already know that it's constant along a streamline, but it could be different values for different streamlines. No, in this case, it's the very same value for every different streamline. Which, if you remember, that's the way we formulated at the time. We made this even stronger assumption. So we say, okay, the fluid has to be irrotational also. Steady flow, ideal fluid, and irrotational. Now you can see it under a different light. So you see that in this case, indeed, so the quantity that is constant, and that's the content of Bernoulli's theorem, is constant every point in space. But this is a slightly stronger assumption, which demands that the fluid is so-called isentropic. Okay. So you see now, you should be pleased to see a kind of generalization. And also we include, you see, the thermodynamic quantities which allows the internal energy to change, with still energy to be conserved, because we just removed all the processes which can dissipate energy or carry it away as radiative processes. Now, let's make a general consideration. Well, let's make this point, which is very important. So, in particular, let's consider a generic quantity, which I call A, a scalar quantity, which is defined per unit mass. And we did it for many thermodynamic quantities that I made before. You see, I just introduced internal energy, enthalpy, entropy, all defined per unit mass. So, in this case, that could be the case. Now, what I'm going to prove you is that the continuity equation, so the conservation of this generic scalar quantity A, defined per unit mass, which, if you think, given that it's defined per unit mass, it means that its density, it's just rho times A, and its flux, it's just its density, rho A times V. And so this is a conservation equation, continuity equation, which states the conservation of generic scalar quantity A. I'm going to show you that this continuity equation is equivalent to demanding that the total time derivative of the same quantity is 0. So the two conditions are fully equivalent. So demanding the conservation of your generic quantity defined per unit mass of a generic quantity is equivalent to demanding that its definition per unit mass, its function per unit defined per unit mass, has a the total time derivative is 0. Let's see why. Well, let's start from the continuity equation and let's develop all these derivatives. In particular, here you have the time derivative of a product, so you have these two terms here. And then you can look at the divergence of this guy here as the product of two terms. A vector field, which is rho v, times a scalar function a. So you first calculate the divergence of rho v, so you can just take a out of the divergence, and then of course you have to do the other way around. So you take out of the divergence rho v, and well, in this case, the divergence of a scalar doesn't make sense, is the gradient. So scalar, the gradient of a. Again, vector calculus identity. But now you can collect, you see, you can collect, in this case, what multiplies rho, so rho, time derivative of a, and here you have rho v scalar gradient of I, so I just collect it here. And then the second and the third term here, you can collect a, so you have this guy here. But if you pay attention, what lies among square brackets is conservation of mass. So this guy here is 0. Continuity equation in the case of mass. So conservation of mass implies that this guy here has to be 0. But this guy here is the total or convective or material derivative of A. So we just demonstrated. If you get backward, you also have the same proof on the other way around. So the two are perfectly equivalent. This will be important for what we'll be seeing in the next classes. Now, let's express Euler equation in a much more meaningful way. To do that, we have to go through some calculations, but it is worth the effort. So in particular, okay, this is just the total, this is just the time derivative of the quantity rho v, of the flux, of the mass flux. Just simple derivative. You derive one and you don't do anything on the other, and then the other way around. Now, let's consider again the continuity equation, so mass conservation. So I just bring the divergence term on the other side. But again, this guy here, you can write it explicitly. So again, this guy is v scalar gradient of rho minus rho divergence of v. Now let's consider Euler equation. Again, Euler equation is something that we already saw. Okay, so I'm not going to comment anymore. Now, let's start from this equation here. You see that the first term here, instead of writing partial derivative of rho with respect to time, I use this identity here. So among brackets here, I put all this guy here, which is just partial derivative of rho with respect to time, times v. So I just copied v here. And this is all this guy here. The second one, rho partial derivative of v with respect to time, I can just exploit Euler equation, if you see. So this guy here is just minus this guy here, plus f minus gradient of b. I just, instead of this guy here, I just exploited this identity from Euler equation. Now, let's write this equation, which is obviously a vector equation, let's write as a function of the generic. So let's project on the ith component. So instead of writing x, y, z, I just write I. I could be x, y, z. Okay? So delta v, the only vector here is v, so vi, ith component. The same works here, so instead of vector v, vi. And look, here within brackets, you have a scalar product. So scalar product means vx times x component of this guy plus. So let's use the, if you remember, the Einstein summation convention. So to mean a sum, we use the same index. So when the same index is repeated, it means a sum over that index. So given that here there's a sum, is vx times x component plus vy times, so we just write vj times the jth component of this guy, but this is a gradient, so the jth component of this guy is just partial derivative of rho with respect to xj. And this guy is a sum, okay? Einstein summation convention, so this is a sum. So j is a muted index because it's summed up, while I is not summed up. Again, the very same here. You see, here I have vi, sorry, should be gradient of vi, and gradient of, because this is the term that gives me the vector character of this term. So I should take, no, that's not correct what I said. This is just the divergence. So the divergence means you take the x component, you derive with respect to the x. So the jth component of v has to be derived with respect to the corresponding xj component. This is the divergence. So again, it's a sum. So this is just the same guy. The divergence of v of velocity written exploiting Einstein summation convention. Okay, very, very powerful notation. And again, yes, here you see we are taking the ith component. So here the guy to be taken, the ith component of is this guy here. So v gradient of vi, but gradient is then scalar multiplied by this. So vj times the jth component of this guy, but the jth component of this guy is partial derivative of vi with respect to xj. And again, this is a summation over j, you see, plus the ith component of these two last guys. So fi, and the ith component is, of course, of the gradient of the pressure gradient is just the corresponding partial derivative with respect to xi. So these are three equations. Three because depending on the value of I, while j is a muted index, is a sum index. Now you can rearrange things. If you pay attention, for example, you see that here you can express, let's focus on the first term, Well, you have a derivative with respect to xj of three terms. So let's see where are they. So when you derive rho, that's the term here. You see you have vi, vj, and the derivative of rho. So again, second, when you derive vi, where is that? Here is the guy. You leave rho and vj unaffected, and you derive vi with respect to xj. Okay, the second case. Finally, you have to consider the derivative of vj. The derivative of vj is this guy here. You see, you have vi rho and the derivative, all with minus sign, because if you see they are all with, they show up in the previous equation, all with minus sign. So that's why minus. So we accounted for this one, and this one. We are left with two guys. You see, here I have the derivative of p with respect to xi. But you can express this guy as with respect to xj instead of xi times delta, the Kronecker symbol, ij, because it's a sum. It's a sum with respect to j, but because of the delta, because of the Kronecker symbol, as a matter of fact, it is as if you were just deriving with respect to xi, which is exactly what we had here. So by putting here p delta Kronecker ij, as a matter of fact, It's a sum, but the only non-zero term is when I equals j. So it's when you derive p with respect to xi. That's exactly what we had before. Plus fi. And just I left it in this way. Why this writing is so meaningful? Because now you see that here you have a vector, well, the ith component of a vector, but here you see among brackets, you have the divergence of, because this guy is a divergence, because it's the sum, because j is a summed vector. So you calculate the partial derivative with respect to xj, and then you sum up. So it's a divergence of what? Here you see you have something which has two indices. So it is a tensor. So it is a rank 2 tensor because it is built by joining two vectors. So 2 rank 1 tensor. So this is it transforms, it works, it behaves like a rank 2 tensor. Mind, rank 2 tensor in the Euclidean space, 3 coordinates, nothing to do with relativity with Minkowski space, okay? So here the matrix is the simplest one, the identity, the Euclidean matrix, and the space is a 3D vector space. But still, it is a vector, it is a tensor, rank 2 tensor. So we can define, and this guy is called stress tensor, and by definition, its I and Jth components are defined like this. And delta Kronecker, the identity matrix, is indeed a tensor as well. So there's no question, this behaves like a tensor. And now you can rewrite, so essentially, what is Euler equation? We exploited Euler equation, so that's where it comes from. And this way, you see, you have, this is a vector field, a vector equation, okay, written, just projected on the ith component, but still it is a vector equation. And you see here, you have the divergence of something, and this something is the stress tensor. So we can use our geometric way of writing, geometric in the sense that it no more depends on the coordinate systems that you use. Much in the same way as you can express a vector as its coordinates or just as a mathematical object which doesn't depend on the coordinates. That's exactly the same, with a big difference, because when you express it as just a number of scalars, so you immediately have in mind a specific reference frame. When instead you don't do that, it means that you are completely free of any reference to any reference frames. So that's the conceptual step that we make from here to here. So this product here that you see is just the combination of two vectors, which makes, which gives you a tensor, rank 2 tensor. If you do it thrice or 4 times or many times, you will have a corresponding rank n tensor, of course. And G here is the metric tensor. So essentially the metric tensor in the Euclidean space, when you just write, it's the corresponding matrix is the identity matrix. So is delta ij. Okay. But written this way is in a more formal way. So we can express Euler equation using the stress tensor, because in this way you immediately recover a meaning, a very much more meaningful expression of the formulation of the Euler equation. Why? Because if you think rho v is indeed the mass flux that we met in the continuity equation, but it is also the linear momentum density, if you think. Rho is the mass per unit volume, so rho v is the associated linear momentum, which is, of course, per unit volume. So rho v has this double meaning. Is also, in this case, what is relevant is density of linear momentum. So this is a kind of continuity equation
in the case of linear momentum, but linear momentum is a vector quantity. So here you have the density of a vector quantity plus the divergence of what? The divergence of the stress tensor. The divergence of a rank 2 tensor is a rank 1 tensor, so a vector. So you immediately appreciate the meaning of the stress tensor. The stress tensor is something whose divergence gives you the stress tensor is a flux of linear momentum, if you think. But much in the same way as when you calculate the flux of a scalar quantity, you need a vector. Now you have to express the flux of a vector quantity. So you need a vector of a rank 2, so a tensor. So the stress tensor is nothing but the flux of linear momentum. And a generic component of this tensor tells you the flux along the ith direction of the jth component of the linear momentum, you see. And you see, this is not zero because we admit the possibility that there is a conservative field, an external field, which is acting. And you know very well that if you have some forces acting on the fluid, of course, the linear momentum content of the fluid can change. So that's why it's a conservation law in a general sense. So if you consider the vector field which is acting on the fluid as something external, well, in that case, of course, it is something which contributes to either decrease or increase the linear momentum, the amount of linear momentum associated with the fluid. But you see that expressed in this way is a much more meaningful equation. So moving on. So far, let's recap what we've done so far. We went through the continuity equation, so conservation of mass. And today, what we've seen is Euler equation. So second law of thermodynamics applied to the fluid element, which turns into conservation linear momentum. So the continuity equation applied to momentum with mathematical difference that you are doing now with a vector quantity. So the fact is something of the higher order, let me say, rank, which is exactly stress. So now we appreciate the meaning of stress. As you can imagine, same to energy conservation. So to do that, we have to figure out what is energy density. So let's define capital D as the total energy per unit volume in this case. So what is that? Well, which term do we have to consider? The first term is the kinetic term. Obvious. The fluid is moving, so it has automatically some kinetic energy. So a given per unit volume, you have, of course, an amount of mass, which is rho. So 1/2 rho v squared is the associated kinetic energy of the fluid. But if you remember, we define epsilon as the internal energy per unit mass. So given that U is per unit volume, the internal energy per unit volume is epsilon times rho. So kinetic energy, so mechanical energy plus internal energy plus what? Well, we consider that we are in the presence of a conservative field, so we can include also in the potential contribution to the mechanical energy in terms of a phi. Again, phi is defined per unit mass. So again, we have to consider when we want something per unit volume, we have to multiply by rho. So this is total energy density associated with the fluid. Now, as I wrote here, it would be tempting to automatically, oh, see, okay, I got the point. Now I understand the game. So whenever you have the density of something, you just take the velocity and you have the corresponding flux of the same quantity. So what I call here GE, the so-called energy flux. Okay, just take the energy density that we just calculated, U, multiply by V, and that's it. And as you might guess from the way I put it, that's not that easy. Why? Because if you do that, you are neglecting a way the fluid has to make work, which is related to expansion. If you imagine you have again, let's focus on a generic ideal fluid element, which is surrounded by some surface, some elementary surface. Let's suppose that this element is at some point expanding. Well, you know that expansion of a fluid doesn't come for free. You have to spend work to do that. In particular, let's suppose that the surface dA, the elementary surface dA, is pushed. It is moving is expanding, so it is expanding with velocity v dt. So sorry, the v dt is just the displacement that is just undergone by the surface element during the expansion. So it means that the amount of work that has to be spent to do that is just pressure times dA, so the force, the elementary force, times the displacement. And of course, because of the definition of pressure, these are parallel. So their scalar product is just the angle is just zero between them. They are parallel. So the amount of work is just PdA, force times displacement, VdT. So it means that the energy spent per unit surface, per unit time, if you divide by dA and dt, is just pressure times velocity. And this work has to be taken into account, which is not, if you follow the line of reasoning, the naive line of reasoning that I was telling you before. So it means that somehow, when you work out the energy flux, you also have to account, again, I showed you here, this is energy per unit area per unit time that you have to spend. There's no way you can avoid it. So it means that in contributing to the flow of energy per unit time, per unit area, so to the energy flux, you also have to add an extra term which accounts for that. So for the fact that a fluid cannot expand for free, it has to spend work. So overall, the flux has to account for it. But now, so if you collect V, you see that you gain inside, among brackets, an extra term of P over rho. But you see, epsilon plus P over rho, this is something which we already know. This is enthalpy per unit mass. So it means that, indeed, the conservation of energy, it looks like, but it's slightly different just because of the extra term that I just mentioned. So it's indeed the partial time derivative of the energy density, this guy here, which we call capital U, plus the divergence of what the flux energy is, which is indeed rho V times U plus the extra term, which is PV. So by collecting all this guy here that I wrote here. So you see that it is the same, the corresponding times V, of course, the same, but instead of the internal energy, you have the enthalpy, as I said, per unit mass. This is really important to remember, because if you neglect that, you neglect the possibility that energy can be exchanged. So the energy content can change just because of the expansion or compression of the fluid. Here I put just a few calculations that whose aim is to show you an equivalent line of reasoning. So let's see more in detail. These are a few calculations, but I think it's really worth, as I wrote here, this is a kind of in-depth analysis that sheds some more light on the possible equivalence by demanding the conservation of entropy and conservation of energy. What is that? Well, I remind you that in the absence of the dissipation processes that I already mentioned, so in the absence of viscosity, in the absence of heat conduction, and when we neglect radiation losses, so entropy is conserved. So it means that if you work out the total derivative of entropy, it means that this guy is zero. In particular, what I also showed you is, if you remember, the equivalence of, if you remember when I said the generic quantity, scalar quantity A, I said, oh, look, if you demand the continuity equation for that quantity, in that case, like the generic quantity A is S, so entropy per unit mass is equivalent to demanding that its total time derivative, so ds over dt, which is this guy here, is zero. The two are equivalent. So this is nothing but conservation of entropy, okay? Either expressed as a continuity equation this way or as a total time derivative this way. So I already proved to you in a more general case, so also in this specific case as a consequence, the validity of this implication, and also the other way around if you want, but in this case we care about this. So this is conservation of entropy both ways. Now, what I'm going to prove you is that in this case, so in the case of absence of dissipation processes and neglecting radiation losses, so when there is no heat exchange, if you demand this guy here, so conservation of entropy is perfectly equivalent to demanding conservation of energy, which instead, in a more general case, of course, conservation of energy is more general than conservation of entropy. You can conserve, energy is conserved even in the presence of radiative losses, even in the presence of dissipation processes, of course. But in this case, so under these assumptions, it is possible to prove that if you start from assuming conservation of entropy, you end up with conservation of energy, which is the equation that I proved you in the previous case in a more in a different way. So let's okay, probably okay. Then I saw some points. So let's remind ourselves we have been saying. So the elementary change, the enthalpy is this guy here, where I reminded you what I did is just both first, second law, thermodynamics. Okay, general. If you divide by dt, you get the corresponding total energy. By simply rearranging terms, so you express the corresponding change in entropy, the question of remaining quantities, you immediately see that this is something like this. Now, if I find that the total derivative of entropy is zero, it is equivalent, of course, that the signification among brackets is zero. But let's write explicitly total derivative is. So instead of total derivative enthalpy, I wrote in this guy here instead of derivative pressure corresponds one. Remember, as much overall. So I just propagated this. Now let's exploit Euler equation. Remind you, Euler equation, this guy here, conservation of linear momentum. Rearranging terms, the idea is that I want to exploit this guy. I want to replace this guy here. So I express minus pressure gradient over rho as a function of the remaining quantity. So I take this guy and put on the other side of the equation. Now, let me replace, instead of this guy here, all this guy here. So I didn't do anything, except for here, you see, I wrote explicitly the definition of enthalpy. So internal energy plus P over rho. This guy is just the same. This guy here is just the same here. And here, as I said, instead of minus this guy here, I just put all this guy here. So I remind you, we are just exploiting. We started by demanding conservation of entropy. And I used now Euler equation here. Now, let's have a look at what happens. Here, okay, I just calculated the time derivative of internal energy. And then what? Well, time derivative of, I leave P, and then time derivative of 1 over rho. And then I should have 1 over rho time derivative of P. But this cancels out with this guy here. So I'm just left with just this guy here. Plus what? Plus V times gradient of W. And I also use this guy here. This is V scalar gradient of. So I can express just as one single term. V scalar is gradient of the sum of enthalpy plus phi. Plus what? Well, let's have a look. Here you have V scalar, its time derivative. But you know it because we used it many times. So this can also be expressed as 1/2 of the square modulus of V scalar V. So this guy becomes this guy here, as well as this guy here. Well, this is a gradient of a vector. So in principle, you should take Vx, and then so the gradient of Vx, if you take the x component, and then you have Vx times its corresponding gradient. This guy here can be expressed as the gradient of V squared. This guy here becomes like this, which looks pretty reasonable. But again, this is immediate to see why this is the case. Okay, just work it out component by component, and you immediately see that this can also be expressed this way here. Essentially because the x component Vx here is then multiplied by Vx here, Vy by Vy, and so that's, and well, this V scalar is the same here. That's where it comes from. Okay. Now, here I just copied the very same equation we've come up with in the previous slide. Now, let's see how we can rearrange terms. You see, you have partial time derivative of different quantities. You have epsilon here and V squared half here. So put them together, you have all this guy here. So this guy and this guy here. Then we have a few terms which are V scalar gradient of. In particular, V scalar gradient of, here we have V squared half here, and here W plus phi here. And then this guy here, we just copied. I didn't do anything, just copied straight away. Now, let's multiply by rho. But you see, here I multiply by rho and I put it within the time derivative. So it means that I have to remove this guy's time derivative. Otherwise, I would have extra term. So the first two terms is just the result of multiplying by the first term. Second, I'm just leaving as is. So it's just raw scalar, and the rest is same. And here I explicitly calculating the derivative of 1 minus 1 over rho squared d rho over t. So minus 1 over rho squared, but I'm multiplying by rho, the equation. So I'm left with minus 1 over rho. And p is because it was really minus because of the result of the. Now, let's see what happens. here I just copied here, here, and instead of the third guy is the third one here, this guy. What I did, I just put rho v inside this guy, which becomes now a divergence. Let's have a look at this here. Well, this guy here is in this, but I have to remove an extra term, which is why. Well, if I take this guy out, that's exactly what I had here. But then it means that I have to remove this guy unaffected times what? Times the divergence of rho v. So these two guys here are just equivalent to this one here. Why is this convenient? One should be, oh, this is crazy. Well, you will see in a moment where this leads. Now let's exploit mass conservation. Mass conservation tells us that this guy here, the divergence of rho v, is also minus partial derivative of rho with respect to time. So by just using this, I just copied this one here. I copied this one here. And see here, I collected all the terms that multiply partial derivative of rho with respect to time. So delta rho over delta t, here I have minus, because there's a minus sign here, minus v half squared, minus epsilon. So this guy here is okay. And then I have here, you see, this guy here, because of mass conservation, is minus delta rho delta t. Minus here, it's plus. So plus all these guys, all the three guys here. So plus v half, v squared half plus. Here instead of w, I wrote it explicitly what enthalpy is. So epsilon plus p over rho plus phi. And then the last term, which multiplies delta rho over delta t, is minus p over rho. Here it is, minus p over rho. Now you see that here in this among brackets here, there's a lot of terms which just cancel out. This guy goes away with this guy with this guy, and this guy with this guy. All this is just a simple, the only surviving term is phi, if you look. Okay, here it's just simply copied. So you can immediately see that this guy is simply phi delta rho over delta t. Now, we are in the study, in a conservative, we are considering conservative fields. Otherwise, we couldn't speak in terms of phi. But by definition of a conservative field, there's no way it can depend explicitly on time. So it means necessarily to be conservative for phi that its time derivative is zero. So it means that this guy is constant with time. So I could just bring it inside the time derivative, and that's the only change that I made. I just copied this guy and just put within. But now you see this is time derivative, so I can just put it in here. And so you see that you can collect rho. You see what we have come up with? This, if you pay attention, that's indeed energy conservation. So now you see in a more algebraic way, if you want, why in the energy flux you have enthalpy instead of internal energy, because the only difference is connected with the work that a fluid inevitably has to do when it expands, or when it contracts. Of course, the sign of the work is different. You see, this is a term which has to be considered. There's no way. And we also see that as soon as you are in the presence of adiabatic reversible transformations, it means that demanding energy conservation is fully equivalent to demanding entropy conservation. And this is something that we will exploit. So at some point, when we will discuss some solutions, some relevant solutions, in the case particularly of shock waves, what the result of a shock wave is in different contexts, at some point I will show you that instead of applying energy conservation, I will use entropy conservation. Now you see why they are equivalent. But I will also make a point, and the lecture today is essentially finished. I'm just making final comments because that's already enough. We saw many things, so I would like you to think about this. The final comment is that when we will be studying shock waves, we'll see that across the shock, entropy is not conserved, while of course energy is. So right across the shock, that's a very special case, which is an exception in this very context that we have been discussing now. So that's a case in which we will not be able to impose energy conservation by using entropy conservation, because entropy across a shock, right across the shock, is not conserved. Because you will see that mechanical energy is dissipated into heat in that case. So you are in the presence of irreversible processes. So entropy across the shock is not conserved. But then when you move away from far away from the shock, so within the shocked fluid, but not across the shock, you will see that entropy is conserved. So the only point at which you have a discontinuity in entropy, as well as other thermodynamic variables, is across the shock. So in that case, when we want to apply energy conservation, we cannot equivalently use entropy, because entropy is not, energy is conserved. But this is, if this comment sounds like something not very troublesome for you, it will become clear. But this is just just to prepare you to all the subtleties. So you see, as the final comment is, let's summarize all the equations that rule the dynamic, the thermodynamic evolution of a fluid, of an ideal fluid, I remind you. So conservation of mass, first equation. Conservation of linear momentum in the absence of an external field. So what you see here is, again, the stress tensor. So the flux of linear momentum. So conservation of linear momentum. And here, conservation of energy. Okay, where you see that you have to pay attention to this. Here, and energy density, internal energy, here, enthalpy. And this table is something that I really strongly advise you to think of, to look at it. Just make sure you give total, full sense to this table. And I would advise you to remember, this is very useful, because if you understand this table, you are fully in control of what is relevant to understand the fluid dynamics in the case of ideal fluids. So you see, for each of the three quantities that are relevant in Newtonian physics and have to be conserved, I put both the density and the flux. So if you, for any quantity, you remember both density and flux, you automatically can write the continuity equation, the corresponding continuity equation, and so the conservation of that quantity. So let's start with the simplest one, mass. The density is rho, the corresponding flux is its density times the velocity of the fluid. And so immediately, the time derivative of the density plus the divergence of the flux, 0. Conservation of mass. Momentum. Look, this guy is a vector. So the density is rho v, which happens to be, you see, the same as the mass flux, but has a completely different meaning as seen in this way. So now this is density of something, and its corresponding flux of something, so the momentum, is the stress tensor, which is defined this way. So the linear momentum conservation will be time derivative of this guy plus divergence of the tensor, which is a rank 1 tensor, so a vector, is 0. Conservation of linear momentum, or F is the external field acting on it. And finally, what we've seen, conservation of energy. So its energy density is this guy, and the corresponding energy flux is this guy, where you have the same except for, but of course, in addition to the velocity term, you have the enthalpy instead of internal energy because of that. So you should understand, you should not confuse. So my final comment is, make sure you do not confuse all the mathematical nitty-gritties, all the details, which is somehow, we are, in this very class, we exploit a lot of vector calculus identities, something which is a little bit, burdensome to some extent. But what I would like you to, not to confuse the mathematical aspect, which is a little bit boring, let me say, with the physical meaning, which instead has to be crystal clear. And in particular, this table immediately is a powerful summary of what we've come up with and what should we remember and what we will be exploiting in next week when we will be studying, when we will be applying in particular all these conservations law to the shock waves, which is the most important topics that we will be focusing on next week. So, do you have any questions?
No, it's all okay.
Okay.